All right, so while you're finding this lesson, a couple of reminders. Okay, remember that the lab we did yesterday is due on the 13th. Okay, so make sure you've got that done. I know a couple of you have already come in and had me look theirs over, which is awesome. Okay. I can do that today after school as well. If you want to pop in, I can have a look at it then, or tomorrow before school. I can also do that. You have your unit exam coming up next week. I will do a unit exam review tomorrow. Okay, in our Friday class, I'll do a unit exam review, and I'll put the review package on Google Classroom today, so that you have that to look at. All right. Okay, so mechanical energy, just quick review here, because we've talked about this a few times already. Mechanical energy is energy due to movement or condition for any object, okay, or system. It is the sum, as a result, okay, mechanical energy is the sum of an object's kinetic and potential energy. Is it possible for an object or system to have both at the same time? What was our example of that? A plane, yeah. Plane flying through the air. It's above ground, so it has potential energy. It's moving, so it has kinetic energy. Okay? It is possible, obviously, to have both. Okay? A falling object has both. So mechanical energy is the sum of your potential, either gravitational or elastic, and kinetic energies. So, law of conservation of energy and work energy theorem go hand in hand, especially when we're dealing with the perfect physical world as we do in Science 10, okay, where no energy is lost to friction and air resistance and all that other stuff. Okay? So when energy is transferred to an object, it can cause a change in both kinetic and potential energy. What do we call this energy transfer? Work, exactly. When energy is transferred, it can cause a change in energy. That's work. Okay? A ball thrown upward has kinetic energy because of its motion. It also has potential energy because of its position. Okay? So it has both. It has mechanical energy. If it has one or the other, it has mechanical energy. Okay, so let's look at a simple example here. I have a 0.30 kilogram baseball thrown in a straight line through the air at a height of 2.5 meters above the ground. All right, so it's 2.5 meters above the ground. It has what kind of energy? Potential. And it's moving at 20 meters per second, so it has, all right, I want to find the object's total mechanical energy. Okay, so to do that, mechanical energy is the sum of the object's kinetic energy and potential energy. All right, so all I have to do is calculate both of those. And we already know the formulas for kinetic and potential energy. So what we have to do is plug in numbers and then add them together. Is that all right with everybody? Yep. Okay, so that's what we're doing here. So we're going to have 1/2 times 0.3 kilograms times 20 meters per second, all squared. Okay, that'll get us the kinetic energy of the ball. And then we've got 0.3 kilograms times 9.81 times the height, 2.5 meters. That gets us our potential energy. So we're adding those things together. Okay, 60 plus 7.36 is 67.4 joules worth of total mechanical energy. As that ball flies through the air in the perfect physical world, okay, it will do this, okay? Because nobody actually throws something in a straight line. Okay? Why not? Why can't you throw something in a straight line? Gravity, yeah. Gravity makes it do this. Okay? You probably noticed this when you were a kid and played with like a hose or a water gun or something like that, right? If you were shooting it, it would always just go down. But if your friend was a little bit further away and you tilted it up, it would go a little bit further. Okay? Gravity always pulls it down, but it makes an arc. Okay? All things that are thrown, okay, fired, shot, whatever, they all follow a projectile arc, and that's because of gravity. So what's going to happen to this object's total mechanical energy as it follows this path? Will it get bigger, smaller, or stay the same? It'll stay the same. Okay? And the reason it'll stay the same is because as it falls, it will also go faster. Move forward too, but go faster. Okay? It'll go faster because what does gravity do to all things that are falling? It accelerates them. So what ends up happening is the potential energy that it had here turns into more kinetic energy, right? So when it gets to the ground, it has no potential energy, but it's all kinetic now, and it's all still there. It just turns from potential into kinetic, right? If I carry something up to the roof and I just hold it out over the edge of the roof, okay, does it have mechanical energy?
No.
Really?
Yeah.
If I hold it out over the edge of the roof, what kind of energy does it have? Right. Is that part of mechanical?
Oh, yeah.
So it definitely has mechanical, right? Okay? And then if it doesn't have any kinetic because I'm holding it, right? It's not moving. But if I drop it, as it falls, its height decreases, its speed increases. It's just a conversion of one form of energy to another, but energy is conserved. Okay? That's the law of conservation of energy. Energy can't be created, it can't be destroyed, but it can be converted from one form to another. Even in the real world, that still happens. Energy is still conserved, it just doesn't turn perfectly from potential into kinetic. Okay? It turns into other things like sound and heat and stuff like that, and it's kind of lost to the surroundings, but it can all be accounted for. Okay? That make sense to everybody? All right, so what I want you guys to try here, or actually let's talk about this example here. All right, let's say the archer draws back this bow. You should never fire an arrow straight up in the air, by the way. Okay? You never fire anything straight up in the air, because what'll happen? Right. Okay. Is that like is it really dangerous? In the perfect physical world, this would be really, really dangerous. Okay? Because in the perfect physical world, that arrow will go all the way up until it stops. Okay? Because gravity slows it down, and then it would fall straight back down. And when it gets back down to here, how fast is it going? Very the same speed you shot it at. Okay? Because all that energy is conserved, right? It gets turned from kinetic into potential, and then it gets turned from potential into kinetic. Take your eye out. Okay? Why doesn't that happen in the real world? Drag, exactly. Okay? As that thing, when that arrow gets to its highest point and it starts to fall back down, air resistance will catch the, what are the feathers called? We'll call them feathers. Things that go on the tails, whatever. Those things on the back of the arrow that make it fly straight and spin. Okay? They would catch the air and then it starts to tumble. Okay? So if it's tumbling, it's turning a lot of its mechanical energy into heat and sound and other things as it falls, and you could just reach out and catch it when it came back down. Okay? Not that you should try this, but the same would be true with a gun fired straight up in the air. Okay? If you fire a gun straight up in the air, the bullet will come back down. Now, you're never going to have perfectly still air where it would fall straight back down and land right back in the barrel of the gun. Okay? Like, that would never happen. And in the real world, the bullet will tumble on its way back down, so it won't go as fast when it comes back. If you did that in a vacuum, it would come back and it would be going exactly the same speed it left the barrel at when it got back. Okay? Because there'd be nothing to take its energy away. So in that case, don't do that. Also, don't be in a vacuum. Also, guns don't work in a vacuum. Because in a vacuum there's no oxygen to detonate the gunpowder. Okay, it's a really bad example. Now that I really break it down and think about it. Okay, so let's have a look at these three problems here. They're really easy. They're what we just did here, essentially. Okay, they want you to calculate either the total mechanical energy, or they give you the total mechanical energy and ask you to calculate the kinetic or the potential. So all you have to remember is this formula. Mechanical energy equals kinetic energy plus potential energy. Okay.
Just like for the equation above, like if it gave a different initial position that was not 0, would you have to do like final minus initial plus final minus initial height or whatever?
Well, it did give you a position that wasn't 0.
Oh, okay.
So no, I wouldn't. But when we get to the next step, which is comparing two different positions, then I have to take into account that while the mechanical energy is the same, the potential and kinetic are different numbers on either side. Okay, we can give you a couple minutes on those three. They're not gonna take you very long. We'll walk through them, and then I'm gonna ask you to do an additional thing with both 9 and 10. Okay, so these are your answers here on the right-hand side for what the question is asking. I'm gonna ask you to do something else, and these are the answers for that. Okay, so don't worry about these ones, just the ones on the right for now.
Still.
Oh, thanks. All right, so for number one, we're just following this formula exactly. We're calculating mechanical energy, okay? We know that it's the sum of an object's kinetic, which the seagull has because it's moving at 8 meters per second, and its potential, which we know it has because it's 30 meters above the ground. The trick to this one is they give you the mass of the clam in grams and it needs to be in kilograms. All right, so all we really change here is we say the mechanical energy will be 1/2 times 0.3 times 8 squared, so that's our kinetic energy, plus 0.3 times 9.81 times 30. That would be our potential energy. Okay, when we put that into the calculator, we should get 97.89 joules worth of mechanical energy. Okay, how many people are still working on number 2? Okay, so for number 2, we've got the high jumper. Okay, and the stuff they give us here is they give us the mass, 55 kilograms. They tell us that they have 3,000 joules of mechanical energy. Okay, and that they're moving at 8.33 meters per second. And of course, if they're moving at 8.33 meters per second, it's probably because they're running on the ground, right? Okay. No, sorry, this is when they're going over the bar. Sorry, so they're going over the bar. So they still have this much speed going over the bar. As a former track and field coach, that's ridiculous. Nobody moves that fast over the bar. Okay, like most people are lucky if they could run that fast in a straight line. But we'll see. All right, fine. That's what it is. Okay, we want to calculate the gravitational potential energy of the athlete. So we know that mechanical energy, which we have, equals the kinetic energy plus the potential energy. So I want to calculate the potential energy. How do I get it by itself? Subtract the kinetic energy. Right. Okay, so I'm going to go EM minus EK equals EP, and then I'm just going to plug in my numbers. This is 3,000 joules. Okay, this is going to be 1/2 times 55 times 8.33 squared. Right? If I do that calculation, that should tell me the potential energy of the athlete. Right, so 3,000 minus the kinetic energy, 0.5 times 55 times 8.33 squared. All right, so they still have 1,091.8 joules of potential energy. Okay, here's the next thing I would ask. In fact, I wouldn't have even asked for that number. I would have asked, how high above the ground are they? Okay, which, if it were me, I would have kind of skipped, or probably not even really done this step. Okay, I would have just done something like this. I would have said mechanical energy, which is a number I already knew, minus EK, which is a number I could calculate, equals M times G times H final. Okay, would I be, or it doesn't even have to be final, just M times G times H. Now I want to find out how high above the ground they are. What do I do with these two numbers? Divide them over to the other side. Okay, which is essentially what we would do with this number. If I divide this number by M times G, will that leave me with the height? Sure it will. So if I want to calculate the height, I'm just going to divide that number by 55 times 9.81. All right, they are 2.02 meters above the ground. That's about 6'7". Right. I coached track and field for like close to 25 years, I can count on one hand the number of times I've seen a high school high jumper go over 2 meters. Okay? Now, an Olympic high jumper, that's a warm-up height, but okay, for a high school kid, that's pretty impressive. Okay? That basically means you're high jumping over the top of the smartboard. It's impressive to see somebody do that. Yeah. Okay, questions on how that one worked? All right. So I want you to try number 3, but I want you to do, or sorry, number 10, the third one. Okay, I want you to do 2 things with that. First, do what it asks, calculate the kinetic energy of the falling hammer. And after that, calculate how fast the hammer is going. Okay, that's the answer. Okay, so that's what I want you to try. Give you a few minutes on that one. All right, let's have a look at number 10 here. So we know the mass is 2 kilograms. We know the mechanical energy is 1,880 joules. We know that the height is 50 meters above the ground. We want to find the kinetic energy of the hammer. All right, so mechanical energy, which we know, is equal to kinetic plus potential, which we can find. So what do I have to do to get EK by itself? Subtract EP. Okay, so that's going to be 1,880 joules minus 2 times 9.81 times 50. So 1,880 minus 2 times 9.81 times 50, 899 joules. Okay, is the kinetic energy of the hammer. All right, if I want to find out how fast the hammer is going, I have to recognize that this number equals 1/2 mv squared, because it is, after all, the kinetic energy of the hammer. So all I have to do now is manipulate for v. So how do I get v by itself? First divide by half of m, right? So that'll be half times 2, so 1. Okay. And then what do I have to do to get v? Square root it. Okay, so the square root of 899 is 29 point something, okay? But 30, basically.
Yeah, it's true.
Yeah. Yep. All right, is that making sense? All right, so that's how mechanical energy works. What we're going to be talking about next is how does the conservation of mechanical energy work? Okay, if this is how we calculate mechanical energy, and mechanical energy can't change, then the mechanical energy of an object is the same number all throughout its movement. So if I drop the hammer off of the building, when I'm holding it off the edge of the building, it has a certain amount of mechanical energy, 1,880 joules, but it's all potential. And then when I let it go, that potential turns into kinetic, and basically they just keep adding up to 1,880 joules. Okay? All the changes is there's less and less potential and more kinetic as it falls. Okay? The height becomes speed, okay? The potential becomes kinetic, and they always balance out. All right, so let's look at this one, because this is where work energy theorem overlaps law of conservation of energy. So I have a force of 100 newtons, pulls back a bowstring half a meter, and the bow is aimed vertically, so that picture we saw on the last page. Okay? How much work is done here? What's 100 times 0.5? Force times distance. 50 joules. Okay? So they gave us the force, they gave us the distance, so all we had to do to find work was force times distance. So we went 100 times 0.5, and we get 50 joules. Okay, that's the last calculation I should have to do. I can answer the rest of the questions without doing another calculation. Why? What's the answer for all of these questions? 50 joules. Okay? The energy that is in the system of the bow and arrow is the result of the archer pulling back the bow and doing 50 joules worth of work. That is all the energy that can ever be in that system. And all that's going to happen is it's going to change forms or convert from one form to another. But the energy itself will be conserved. That is, it cannot be created or destroyed. Okay? So once I put the 50 joules worth of work into the bow, okay, and I hold it there, there's now elastic potential energy in the bow. 50 joules of it. Okay? How much kinetic energy does the arrow have the instant it's released from the bow? Well, when I let go of the bow, the string exerts a force through a distance on what does the string push on? The arrow. Okay? It exerts exactly the same force I did to pull it back over exactly the same distance. Okay? Pushing all 50 joules worth of energy from potential in the bow to kinetic in the arrow, 50 joules. Now, that arrow was aimed straight upwards, so as soon as it leaves the bow, it's now starting to slow down. Okay? Eventually, it'll get to its maximum height, where its speed will be 0, and its potential energy will be 50 joules. That's all the energy that can ever be in that system. Okay? Does that make sense? Right? That's the law of conservation of energy. Once you put the energy in, okay, it can be converted to other forms, it could be transferred to something else, but it's always going to be there. Okay? We can't create it, we can't destroy it. All right, we already did those ones. Okay, so here's what we're saying about the law of conservation of energy. We are saying that since it can't be created or destroyed, that our mechanical energy final equals our mechanical energy initial. Okay? It can be converted from potential to kinetic, but it can't be destroyed. So, as we were talking about with like dropping the hammer off the top of a building, okay, whatever we have at the top of the building that's all potential is all we'll have when it's at the bottom, and it's all kinetic. Okay? I hold it out there, it's got potential energy. When I drop it, the potential turns into kinetic. The instant it hits the ground, okay, it has exactly the same amount of kinetic energy as it had potential energy at the top, because energy is conserved. Okay? So, I want you guys to write this example down here. Okay? I have a 1.5 kilogram rock, and it's dropped over the edge of a cliff, 30 meters above the surface of a lake. We want to find the speed of the rock just before it strikes the surface of the lake. Okay, so I just want you to write that problem down, then we're going to walk through the solution. And you actually have the solution in your notes package, but I want to walk through how to get it. So in a case like this, I get kind of similar information to a work energy theorem question. I'm getting heights and speeds and stuff like that. Okay? But what I have to recognize here is no work is being done here. Because the amount of energy at the beginning and the amount of energy at the end are the same. If work was being done, then there would be a change in energy. Okay? The other thing I have to recognize is nobody ever mentions force anywhere in this question. Okay? And every work energy theorem question has to mention force, because it's force times distance, and there's going to be a change. There's no change here, so there's no force. Okay? So here's how I want to start this out. I want to write down the law of conservation of mechanical energy mathematically. Energy initial equals energy final. Okay? Mechanical energy initial equals mechanical energy final. All right. How do we calculate mechanical energy again? That's what? Kinetic plus potential, right. So what we're saying here then is that the initial kinetic plus the initial potential equals the final kinetic plus the final potential. All right. At this point, I want to look at the context of the question. It is possible I don't have all 4 types of energy there. Okay? So a rock is dropped over the edge of a cliff. How fast is something moving the instant I drop it? That's how fast it will accelerate. How fast is it actually going? 0. So when I'm holding it out over the edge of the cliff, does it have any kinetic energy? Okay, then it doesn't have any of that. Similarly, when it's just about to hit the ground, its height will be 0. So it doesn't have any of this. Right, so I can eliminate that, okay, right from the context of the question. The other stuff I'm given, the mass, 1.50 kilograms, which actually will make no difference whatsoever, okay? And the height, initial, 30 meters, right? We are looking for the final speed of the rock. Right, and I kind of said something that might have confused you. I said that mass won't even matter. Why will the mass of that rock not affect how fast it goes? Remember the feather and bowling ball video we watched? We're working in the perfect physical world. Do all things fall at the same rate? Yes. So the mass won't matter. In fact, it's going to cancel mathematically when we start moving things around. Okay? So right now, what our formula is saying is the initial potential energy is equal to the final kinetic, which we've talked about already. Okay? It's going to convert itself from potential to kinetic, and all of it will still be there. All right, do I have a formula that solves for potential energy?
Yep.
Do I have one for kinetic?
Yep.
Okay, I want to solve for VF. What do I have to move? I don't want to move V. I want to leave V where it is. Half of M, right. What happens here? Right, because all things fall at the same rate. Now, what would be different, where mass would matter, is if they asked me to calculate the energy. Then mass would matter, because the bigger something is, the more energy it has. But in terms of its speed is not a function of its mass. So mass actually goes away. Okay? All right, so I have G times HI divided by 1/2 equals VF squared. What do I want? Just VF. Okay, so I'm going to have the square root of G times H initial divided by 1/2 equals VF. Okay, so that'll be 9.81 times 30 meters divided by 1/2, all square rooted. So 9.81 times 30 divided by 0.5. Square root. All right, so that rock will be moving at 24.3 meters per second the instant it hits the lake. All right, everybody okay with what we did there? It's mostly algebra. Right? It's just a matter of figuring out what I have and moving it all around to get what I'm looking for. Okay, so when it comes to law of conservation of energy questions, they're a lot like work energy theorem questions. They're very patterned. Once you learn the pattern, they're pretty much all the same. You just have to solve for the right thing. Okay? Now, in terms of your algebra skills, these are the ones that will tax your algebra skills more than any other. You have to move a lot of stuff. This is as easy as they get. Okay? I have EP equals EK. I didn't have any other kinds of energy. Okay? When we get to more involved ones, they'll have both. They'll have all four. There'll be numbers for all four. And we'll have to do a little bit more manipulating. It's not tough, just more of it to do. Okay? All right, so 24.3 meters per second was our final answer there. Okay. All right, number 11 works pretty much the same as that. So try number 11, see how you do. All right, so from the context of the question here, we know we have a 10 kilogram water balloon. Okay, and it's dropped from a height of 12 meters. So that would be my initial height, because that's where it starts from. Okay? And we want to calculate the speed just before it hits the ground. Well, that would be the final. Okay? So those are the the two things I'm given and the third thing I'm looking for. All right. Since there's no forces, it doesn't say anyone threw it, they just dropped it. Okay? Is there any change in energy going on? Okay, then energy is conserved. And as a result, our initial and final mechanical energies are equal. So that's going to mean initial potential plus initial kinetic equals final potential plus final kinetic. Can I eliminate any of those? Yes. Since it was dropped, my initial velocity is 0. So my initial kinetic energy is 0. And since this is talking about when it hits the ground, my final height is 0, so my final potential is 0. Right? Which greatly simplifies what I have to do, because now I have 2 less things to write in there. All right, formula for potential energy. M times G times H initial equals 1/2 mvf squared. Am I writing the same thing over and over and over again here? I am. Okay. First I said mechanical equals mechanical. And then I said mechanical, which is this plus this, equals mechanical, this plus this. And now I'm saying the same thing here. Just some of my things were 0. So, okay, I'm still saying EI equals EF all the way down. All right, so I am looking for the final speed. So that means I need to divide both sides by half of m. Now, if you're not comfortable canceling m, leave it in there. It won't affect your answer at all, okay? Because mathematically it's going to cancel anyway, even if you plug it in. Okay, and then I need to square root this. So VF will be the square root of 9.81 times 12 meters divided by 1/2, all square rooted. Right, which should give us 15.3 meters per second. Okay, questions on the first one? All right, try the second one. You're not looking for speed now. It's giving you speed. Now they want you to find the height to which the child will rise. It's still top and bottom. It's still comparing top and bottom, so that part of it is still the same. No. Yes. Okay, so for this second one, right, we know our initial height is 0. Okay, we have to assume that. This is one of those trampolines that's actually like right at ground level. They bury the legs, they dig a hole and put the trampoline right at ground level. Okay, so our initial height is 0 meters. Okay, we're looking, we know our initial speed and we know our final speed. Our final speed is 0 meters per second. That's what we were talking about a minute ago when you throw something up in the air. And we know that our initial speed is 1.6 meters per second. Not very fast, it's a little kid. Right? So we are looking for the final height of the child. There's no forces involved, okay, it's just gravity, so EI will equal EF. Okay. Initially, I would be on the ground where I would have no potential energy, so my EP initial is 0. I do have kinetic energy initial because they tell me the kid's moving at 1.6 meters per second. At the end, I would definitely have potential energy because they'll be further up in the air, and my kinetic energy will be, when they're at their maximum height, it'd be 0, right? Because they're not moving there. So we've got our initial kinetic equals our final potential, kind of the flip-flop of the first two we did. So we've got 1/2 mvi squared equals m times g times hf, and we're looking for hf. So how do I get hf by itself?
You divide by mv.
When I do that, the mass cancels, okay, left with hf, and all I have to do is go 1/2 times 1.6 squared divided by 9.81, and I get 0.13 meters. It's a little kid. Okay? I'm not going to go very high. I mean, think about it. They left the trampoline at 1.6 meters per second squared. In 1 second, due to gravity, your speed changes by 9.81 meters per second. It means that you're not getting very far off, okay, off the trampoline if you're only moving at 1.6 meters per second. All right, we're gonna leave it there for today. I will post your exam review probably right after class here, and tomorrow we'll do our unit exam review, and then Monday we got a lab. Tuesday, finishing this up and talking about efficiency. Wednesday, finishing everything up. Thursday, test. All right. Okay, good job today, guys.